So, good afternoon. My name is Michał Piłowaczy, and I will be the host of this week's session, which is about structured materials and how to use old school computer graphics to generate novel 3D printing materials. And it is my great pleasure to introduce our first speaker, which is Sylvain Lefebvre, a senior researcher at INRIA, where he leads the Mother from Graphics team, and his work focuses on algorithms for generating and processing complex shapes in additive manufacturing and computer graphics. He enjoys writing software and making and hacking things. And especially for this week, I have a small announcement. Sylvain will have to leave shortly after his talk. So if you would like to ask him any question, please do so during his talk. And then we will have a short Q&A afterwards. And then we will continue with the deep dive from Thibault. And Sylvain, the floor is yours.
Thank you very much. So it's a great pleasure to have the opportunity to talk to you today. So I would like to thank the organizers for making this possible. So for this motivational talk, I'm going to present something that I'm very passionate about, which is the link between computer graphics and what we do in advanced 3D printing. And in particular, old school graphics, and I will come back later in the talk to what I mean exactly by that. So first, let's talk about what is the link between graphics and 3D printing. And I'm sure we all have our own point of view on this. But to me, it really boils down to the fact that 3D printers are screens. And in some cases, they are quite directly screens. For instance, these resin printers here are directly projecting an image onto a resin that will solidify where there is light. And the one on the left is using a DLP projector, and the one on the right is using an LCD screen to mask out the UV light where the resin should not be solidified. And so that means that in a way you have a 3D screen, or rather you have a 2D screen that is sweeping through space, and the sweep of course comes from the platform or the bed of the printer, which is moving up as you generate the layers. And because you proceed layer by layer, this is a discrete sweep, but some printers can also do a continuous motion for that. So you might be wondering then, how about the printers which are using trajectories or toolpaths? And for instance, these are printers which are printing out of filaments that is being melted in a nozzle. And then, this filament is deposited and solidified along trajectories, or this can be a SLS system where you have a powder bed and a laser that goes along the powder to solidify it in different places. Well, it turns out that these type of printers, they also relate to computer graphics, but to the early computer graphics, where screens were basically drawing lines. And here I'm showing two examples, which is the Vectrex game console and the Asteroid arcade cabinet. And in both cases, these are using vector graphics, where XY controlled electron beam is directly drawing lines onto the screen. So the basic primitive is not a pixel, but it's actually a line. So it's quite interesting to see how, in fact, these trajectory-based printers are really relating to the early graphics from the 70s and the early 80s, and to all the algorithms that were developed during this time. So of course, you can see 3D printers as screens, but there are very specific screens, right? So first, there are huge screens and there are slow screens. So why are they huge? Well, if you think about what will probably happen in the 5 to 10 next years, we're probably going to consider micron scale details in metascale parts. And so that's 2 power of 60 bits if you just put 1 bit per voxel, and that's a lot of data, right? Roughly 1 exabyte. So that's way too much even by nowadays standard. But of course, this screen is fairly slow because we are creating things 1 layer at a time. And when I say slow, I don't mean in terms of human perception time, right? Of course, right now, this is even slow for us. But even if you multiply the speed by 100, which would be great, it is still fairly slow compared to the computational power we do have right now and we will have in the future. And this brings up an interesting common point with old school computer graphics. And to understand why and how, let me tell you about the Atari 2600. This is a video game console, which was a big milestone in the history of video games, and that was released in 1977. It had a 1 megahertz processor, which back in the days was fairly reasonable. In fact, some other computers released later, like a couple of years later, like the Commodore 64, had a similar processor. But then it had only 128 bytes of memory, right? And I'm not making a mistake here. That's 128 8-bit numbers. I'm talking only about the RAM, the writable memory, because the ROM was in the cartridge, and of course, these were several kilobytes. So the thing that is interesting here is that this console was still able to generate a picture which was 160 by 192 pixels. But when you think about it, with 128 bytes of memory, there is absolutely no way you can do a frame buffer. So the only way you can draw this picture and make something graphically interesting it was to compute the pixel values as the picture was being displayed. So as the electron beam is drawing the pixels on the screen, you have to compute what the next color of the next pixel is going to be. You cannot store this in memory. And this is called, in old school graphics, racing the beam. And there's a very interesting book that has been written precisely on this topic on the Atari 2600, and I highly recommend reading it. It really pays tribute to what it meant to be developing games for such consoles. Very interesting stuff. So how does this relate to 3D printing? Well, we can be racing the beam in 3D printing. And in fact, many techniques just do that. And the idea is, as you are fabricating one slice after the other, you can just compute in memory what the next slice should be, send it to the printer, then forget about it and move to the next slice. And so this object that you see being fabricated on the right-hand side actually never entirely exists in the computer memory. It only exists when it's instantiated in reality as a complete object. And so the idea goes as follows. You start from an envelope, which is maybe your 3D model, let's say a STL file. You slice it, you get one image of a slice, and then you call this procedure or this process that will generate the details within the interior, within the area of the slice. And you do that only for the current slice. And of course, it takes some specific ways to build this process to be able to do that. Then you send the slice to the printer, you forget about it, and you move on to the next one. You only have to be fast enough so that the printer doesn't have to wait for you, even though maybe it could, but it's really not good to interrupt the printing process. And of course, it's something that has been recognized by several researchers in the field. And like I said, there are quite a few methods using this idea. Another topic that is relating, that is a shared common thing between graphics and old school graphics and 3D printing are tile-based graphics. So back in the days, you did not necessarily have enough memory to store the entire image of the game level you wanted to produce. So one thing that was very common was to create a set of tiles. These are basically small building blocks, typically images, and then to describe in a tile map how to arrange these different tiles in space. So here in the tile map, every number is the index of a tile that is on the left. And you would typically, either in software or with hardware support, you would be able to draw on screen the image, which is the assembly of all these tiles according to the tile map. So this had two immediate benefits. The first one is that, of course, you could describe very large scale levels without using a lot of memory, because you're decoupling the fine scale details, which are now the tiles, from the coarse scale layout, which is now the tile map. But it's also great for authoring, for game designers, for level designers and texture artists, because now they can assemble levels like a puzzle, which is much easier than having to paint every single individual pixel. And for this precise reason, this methodology is actually still used under some form, even in modern games nowadays. So how does it relate to fabrication? Well, sure enough, there's exactly the same concept in fabrication, where we are optimizing things at a coarse scale, and then we're instantiating a material by choosing tiles from a dictionary of tiles that have been pre-built. And of course, the tiles have to have matching boundaries because they need to create a coherent piece of material and to connect properly one with the other. Interestingly, this idea also finds roots in mechanical engineering, where researchers have been studying what would be a tile that, once periodically repeated in space, would give some average behavior. So the idea is to optimize the tile content so that when it's periodically repeated in space, considering an infinite domain, it would achieve some behavior, or some average behavior. And this, of course, is directly related to the theory of homogenization, which is this idea that your heterogeneous material, if you have enough of it, is going to behave as some sort of homogeneous, as an homogeneous equivalent material. And this is a very important idea, because by decoupling the coarse scale from the fine scale, you can now have optimization processes which are only working at a much coarser resolution, so they can be much more efficient. And also the optimizer can consider an average material instead of worrying about the fine scale details of the actual final structure. But the question will be, how do you instantiate a material out of this solution? knowing that these solutions very often are actually not simply about density. In every point of these domains, you get an elasticity tensor, and you can also have, if you choose so, you can also have information about the anisotropy, for instance, of the material. And so the tiles that I showed before are not super convenient when you actually have changes of orientations like that. So it's a very interesting problem how you get from this coarse scale solution that is more general and has also a directionality in it to an actual structure that will implement this. And the first time I came across this problem, this was in a presentation by Oliver Pons, who was describing work he was doing with colleagues at the time about generating periodic structures that would follow this orientation and scaling fields. And of course, this is a perfectly fine way to approach this problem, which in graphics relates to quadrangulation and hexahedral meshing. But when I saw that, I was thinking, maybe there's a different way this can be approached. And in particular, with my, old school graphics intuition, I thought that maybe procedural textures would be a great way to answer this problem. So you might be familiar with procedural texturing, and this is this idea that, if you don't have enough memory to store the details of the scene you want to render on screen, instead of storing stuff in memory, you can compute it when you need it and where you need it as you render the image. And this was, of course, introduced by Perlin and Musgrave and several computer graphics pioneers over the years. In this case, I'm not so much interested in this possibility of trading off compute versus memory, even though that's very convenient for racing the beam as we saw before. The reason procedural textures are the good choice for this problem, I think, is because they offer a lot of control. When you propose to texture artists to create a texture by combining computational primitives, you need to find ways to expose controls to them so that they can express the kind of appearance they are trying to do, like marbles or mountains or water or whatever it is. And it turns out that we've worked on this problem with Ares Laguet and other colleagues back in 2009, and we proposed a pattern generator, which is a basic building block for procedural texturing that is able to generate oscillating patterns, wave-like patterns, this is what you see on the right, according to direction fields, this is what you see on the left. And so that's a procedural texture. It has all the benefits of a procedural texture, but it can create this kind of elongated oscillating patterns. And this triggered a whole direction of research within our group, and we've made several methodologies along these lines. And what Thibault will talk about later is actually one of the most advanced techniques we came up with in this direction of research. And just to show you an example, here is work by my colleague Jonas Martinez, together with Bert Geoffroy and Grégoire Allaire, where they were able to instantiate this homogenized topology optimization solution as a sort of foam which generates anisotropy, right? And the idea, of course, is that by exploiting this anisotropy, for the same amount of material, you get something that is more optimal and that will be more rigid for the weight you are using, thanks to the orientation of the beams inside. All right, so I could go on and on, but there's another common point I want to mention between additive manufacturing and graphics, which is a fun project that we did some years ago, where we looked at anti-aliasing, right? So anti-aliasing in graphics is this idea that if you want to draw these polygons that you have on the left using only pixels, if you only sample at the center of the pixels and choose to either put some color or not put some color in the pixel, you get this aliasing defect, which is a staircase due to discretization, of course. And as we know in graphics, a better way to do that is to consider the integral over the pixel and to see what is the coverage of the polygon within the pixel so that you will put the color that corresponds to the ratio of coverage. And this generates the anti-aliased image that you have on the right. So how does this apply to 3D printing? Well, we're looking at this 3D prints using filament printers. And here you're looking at a cross-section of the trajectories, which are orthogonal to the screen, right? And when you look at this, they sort of form pixels in this layout. This is an optimistic layout because in practice, they never quite perfectly align like this, but it's just for showing the idea, right? And the idea here is to say the size of these things, or to say it otherwise, the height of every trajectory you deposit should correspond to the amount of material that's above. And here we're clearly missing some amount of material. And so we can, in a sense, correct the height of every trajectory so that we better represent the amount of material that's above. And of course, when you do that, the passes become slightly curved. You have to worry about minimal and maximal thickness, but everything checks out quite well. There are some complexities in the ordering of the passes to avoid collisions and so on. But you can get very nice results for, in fact, very little overhead. And here what you see at the bottom are two prints. Both are using 0.6 millimeter layers, but the right one is being anti-aliased in the way I just described. And so that's a huge quality improvement for like very little overhead in computations. All right, so for the end of my presentation, I would like to come back to this notion of old school computer graphics and what I understand by this, what it means to me. When I say old school, there's old here, right? And so when is old enough, for instance, what is a new technique and an old technique? In fact, it doesn't really matter to me. When I say old school graphics, I don't really refer to a period of time. To me, it's a mindset. It's a way of approaching problems. This means, what this means for me is the first thing that is important is that it's a mindset where you try to do as much as possible given constrained resources. Back in the days, of course, the computers were very limited. We wanted to generate complex pictures. We had like so little memory and so little computational powers. Researchers needed to find all sorts of interesting and unusual ways to sort of fake these details or obtain this detail without using much more resources. And so in a way, this is about being parsimonious and trying to use as little hardware and software as possible for your objectives. Nowadays, we're sort of losing this, and I'm the first guilty of that because our computers are so powerful. I don't even think we truly realize how powerful our desktop computers are becoming because it's beyond what we can really fully comprehend. And what's more is that we have the cloud systems where you just can spin a new instance if you're running out of resources, right? And so it gives us this problem where we don't really feel the limits anymore, right? We're never sort of facing this wall of reaching the limits of our hardware and software. And I think that's problematic. And perhaps we want to reintroduce some of these limitations and impose them to ourselves so that we can try to be more parsimonious and use less resources, less compute power, less hardware, less energy, of course. And when you look at what people do, for instance, in the shader scene, they do exactly these kind of things, and that's true as well of the demo scene, of course. For instance, I'm really fascinated by these shaders that fit in a single tweet. So that's just a few characters where you first have to make your graphics using a pixel shader, which is already a constraint, but then it has to fit in this very small character budget. And you get like insane effects. People are able to do very, very impressive stuff. And when you think about it, like the per character value in terms of getting the result is incredible here. And I'm not saying this code is portable and easily readable, right? For sure, it's not. But it's really intriguing, right? And I think it's a good objective to try to really achieve as much as we can with as few resources as possible. And also, and this one is funny, right? I think it's about being non-traditional. It's funny because if you look at the definition of old school, if you ask Google, it will tell you this is like, praising some old and traditional way of doing things. But to me, old school graphics is quite the opposite, right? These are computer graphics from an era where there was no usual way of doing things. When Henri Gouraud proposed to interpolate the lighting value so that you could fake the perception of having a curved surface, this was completely groundbreaking, right? Before that, we were just trying to add more and more and more triangles, hoping for the best. And so you had to invent ways to go beyond these limits, which were completely different from what other people were doing. And I really like this idea, and I think we want to be doing much more of that. And also, something I really like about old school graphics is there were a very clever way to constrain a problem to make it more approachable by, just adding some constraints on your solutions. And let me take an example, which is a big driver in my passion for computer graphics, and that's Doom 1993. And probably you're familiar with the game and with the BSP rendering of it and so on. But to me, the smartest decision that was made in the design of the game was to impose a constraint on the level design that every level, as seen from above, would be a 2D map. And don't be mistaken, this is a 3D game, right? There is an elevation to the floors and to the ceilings, and so when you walk through the level, you feel it's a 3D level. But because the level is constrained to be 2D as seen from above, there are many very nice optimization you can do in the rendering, and you can make a very efficient rendering. So by constraining your problem and your solutions without trying to lose too much in terms of what you get in terms of result, you can really make things simpler and fit in tighter resources for your particular problem. And there are, of course, plenty of other examples in computer graphics and in research. So how do we stay old school? I think it's important that we keep welcoming works that do the same as a work that has been published before, or 90% of the same, but is using much less resources. Or maybe works that explore different ways to do the same as something that maybe do not improve on the result, but they have a completely different point of view. And in my experience, these works are hard to review because it's hard to judge, when is this good enough? When is this different way of doing things is interesting enough? It's difficult, but I think we really want to try to do that because we want to encourage people to strive for simplicity and low resource usage. And don't get me wrong when I say that. Complex is fine, right? There are things which are inherently complex and we need complex solutions for them. And that's perfectly justified in many cases. Also, in some cases, you need to start complex so that you can progressively refine and become simpler and simpler because, doing simpler, elegant things is actually a process and it takes time to stumble on it. But I think the important thing to me is we should all keep in mind this question, right? Maybe there is a simpler way. And that's something that really keeps me awake at night and keeps me excited about doing computer graphics. So thank you very much. Of course, I mentioned the work of many collaborators. So I would like to thank all of them. And I will, I think, take a few questions now. But if you want to reach out by email or through Twitter, please feel free to do so. Thank you.
Thank you very much for your inspiring talk. And I will start with one question that I had when you were talking about chasing the beam. Mm-hmm. In certain 3D printers like FDMs, it is possible to not only print layer by layer, but also lift it to the 3D. So Absolutely. How could we chase the beam in such a case?
Right. So it's interesting. I actually had a slide that I removed in the interest of time that was talking about our work on one of our work on curved slicing, where we're actually curving the slices by deforming the space, which means in fact it's still flat, right? In some space. So you could do exactly the same, but of course you can also go. You can raise the beam at the trajectory level. You don't have to do it per layer. You might not even need the concept of layers, right? And you can just see that as a gigantic spaghetti thing, right? Which is fun to think about. And then it's really a problem of how fast you can do this, how good you will be at predicting the future. By the way, when you raise the beam, it doesn't mean you can't do any preprocessing, right? Maybe you can do a little bit of preprocessing, and then you have all these trade-offs, right? It's very interesting to explore.
And the second question I had was relating to the power that we have currently. So, while we do have progressively more powerful computers, we are also having progressively smaller and to some extent still extremely powerful computers like the Arduinos. And I wonder if this would not be a nice constraint for the computational budget.
It is absolutely. In fact, there's another slide that I removed, which was about some work I do around FPGAs, and I think for me, the way I'm recovering from this loss of understanding of where the limits are is by building my own computers on an FPGA, and this is a great adventure. If you're interested, please reach out to me. And it makes you understand, like, actually 1 megahertz is a lot, right? It's 1 million clock cycles per second. So of course, gigahertz is completely mind-blowing, right? But just getting back to the roots and realizing that 1 megahertz is already a big deal, 100 megahertz is a huge deal, 1 gigahertz is insane, right? And so we should be able to do things which are, like, I think, much more than what we currently do. But it's hard as well, right? To like getting the last amount of power from every processor requires a lot of work, right? So of course, it's also perfectly understandable that we would spend some of this power to make things more stable, more reliable, and so on, right? It really depends what you're doing. Yeah.
Well, thank you much for your talk and for staying for us some questions. And Sylvain will be also available via email in case somebody would like to discuss with him further on any of these topics. And I would now like to introduce our second speaker, which is Thibault Tricard. He's a student of Sylvain, and he's from also INRIA Nancy, where he works on the link between additive manufacturing and computer graphics.
Right.
So the floor is now yours.
Thank you. Just let me share my screen. Is that okay? Do you see?
Yes.
Okay, perfect. So thank you for the invitation first. So today I'm going to talk about procedural noise pattern for additive manufacturing. Right. Okay, so I have a small problem here. Okay. During this presentation, the different part will be indicated with color symbol. Right. And I'm going to start now with a bit of an introduction and previous work. So as you all know, additive manufacturing allows us to create objects from 3D models. Typically, this is done slice after slice. Here you have an example here. And during my work, I choose to focus more on fused deposition modeling, which is a way to deposit melted matter along tool passes with nozzle. And once the tool passes cool down, and so the matter is solid again, we can print on it to accumulate matter and create shapes. Usually we do that by slicing the object and working in 2D planes on which we define tool passes. So here you have an example of what a slice could look like. And inside, as you can see, we have the contours that will form the final shape, and also some matter inside that we call infill. So infill can get many shapes. Here you have different examples, from very simple one, which are 2D pattern extruded, to more complex one that can have interesting shapes. Right. So infill is very practical because it allows us to use less materials than if we printed the part fully, and it also helps us print quite faster. However, while doing infill, we have to take into account for collapses, for example, and this actually gives us, like in this example here, where the infill is not dense enough, and so some part might collapse. And this actually gives us a great opportunity to optimize infill. As you can see here, we densify a bit the infill close to the part that were problematic before, and so now it's okay. And this leads us to what we call inverse design. So as Sylvain explained a bit earlier, inverse design allows us to optimize a shape so that it matches the property we want. For example, this work by Prévost and colleague, where they optimize this dragon to balance it, and so that it can stand on its foot. And as you can see, the optimizer remove matter inside the head so that it can be balanced. This can be also used for other problems, such as stress reduction. So here, Wu and colleague optimize this bone so that it can withstand the typical stress the bone withstand in our body. Right. And all those methods are part of what we call full-scale topology optimization. So these are methods that discretize the object in finite elements and will optimize the density of each finite element so that we get the property we want. This can be used to create very impressive objects, such as this one by Agaï and colleague, where they optimize the full wing of a plane so that it can withstand typical stress this wing withstand in real life. We can also do that to create a bridge, as here, with this bridge that is actually in place in Amsterdam, and then you can walk on. And so one of the main problems of this approach is that you have to discretize your object in finite elements at a very fine level to get really good results, so that it can be a bit of a problem. To go around that, researchers proposed to do what we call multiscale topology optimization. So Sylvain talked about that a bit earlier. So basically, you will optimize your object at a much more coarse level, but you will optimize for fields such as density, orientation, or whatever. And you will use this information and give them to what we call geometric infills, so that they generate the fine details of the infill. Geometric infill can have many shapes. Here are a few examples by Panetta and colleague and Pasco and colleague. Those examples, for example, can adapt for density here. But the problem is with these patterns that they don't really follow FDM constraints. Typically, for example, they are formed with beams that does not print well in FDM, and also they have part of the shape that is not well supported. So to go around that, researchers such as Kuiper and colleague propose to design infill function such that they strictly enforce a manufacturing constraint. So you have an example here that allow you to control the density of the infill you want, and that result in very flexible material. Other researchers such as Martinez and colleague propose to use a geometric function that lets you control density, orientation, and directionality, right? And they actually achieve that in a very scalable way because they use a procedural methodology as explained by Sylvain earlier, such that in each they will be able to compute each slice independently. And during my work, my main focus was trying to control this direction and the directionality of anisotropy. So this can be very important as demonstrated by Anne and colleague, where in their work, by carefully choosing the orientation of deposition, they were able to use the anisotropy of its response of the material, such as it bend in a predefined way to get when presented with it. This has also been used in this work by Jordan and colleague that use the filament to constrain some distance onto the material, and so to constrain also its deformation. This also will be used to create inflatable objects, such as this one by Panetta and colleague. And of course, we can fairly imagine that if we are depositing carbon fiber inside the material, the orientation of deposition will be fairly important. And we wanted to do all that while keeping all the control that was previously provided by Martinez and colleague, and keep also the scalable approach and the procedural approach. So to recap, our main objective was to create procedural infills that are strongly oriented and highly controllable. So why is that difficult? So to understand a bit, we have to go through procedural texture. So in computer graphics, a texture is usually just a 2D image that you will map on the object so that it affects the object appearance, right? But if you have very large texture with very fine detail, it can be quite heavy on the memory. So to avoid that, researchers proposed to replace this large 2D image by simple functions that you can evaluate in each point, and that usually cost a lot less. This procedural texture can generate a lot of different patterns. Here you have a few examples with cloud, marble, caustics, and even sometimes with full scene generated only with function. And a key building block for this procedural texture are procedural noises. So basically, it's how to build this F function that generates the texture. Here you have an example where I mixed different noises so that it creates an interesting texture. A thing with procedural noise is that historically they have tried to produce very high quality band limited isotropic pattern in the Fourier space. So here you have an example of noise, and they are Fourier in the power spectrum. And as you can see, the isotropy will appear as a ring in the Fourier space. But if we look back at our main objective, which was to create something that was strongly oriented, we can see that isotropy is not the best choice here. So instead, we went to anisotropic noise that can create an anisotropic pattern. And we choose to focus on the Gaba noise, which is one of the last one from this category. So I'm going to go a bit into detail in Gaba noise because it's fairly important for our work now. Right, so Gaba noise will look a bit like this. So it creates this wavy pattern as introduced by Sylvain a bit earlier. And as you can see, this power spectrum creates two lobes of energy that indicate that it's quite anisotropic. And this noise relies on the sparse convection noise that you can generate by generating first a distribution, and then on each point of the distribution, apply a kernel. And what is really nice with this theory is that given the distribution follows certain properties, the spectrum of the kernel will be the spectrum of the noise. So now let's look at the Gaba Noise kernel. So it's composed of a Gaussian multiplied by a sine wave. And when you combine them, you get this kind of wave here. And in 2D, it will look a bit more like this one. So if we decompose it and look a bit at its spectrum, we'll see that it's composed first of a sine wave. So in the Fourier space, it will be just two direct positions according to the frequency and the orientation of the kernel. And of a Gaussian, that will also be a Gaussian in the Fourier space. And so as we multiply Gaussian by a sine wave in the space domain, in the Fourier space, it will be the convolution of the two Fourier transforms. So in the end, our spectrum will be two lobe of energy, two Gaussian in the spectrum, positioned with the frequency and the orientation of the kernel. And here you have an example of the noise in its spectrum. And here you have another example where I put the kernel on the side. As you can see, the kernel is oriented the same way as the power spectrum and as the noise. And if we rotate the kernel, the noise rotates, and the same rotation will appear in the power spectrum. And nice thing is that if you combine different kernel, the power spectrum and the noise will be the combination of those two kernels. So as I said, Gaba Noise can generate this wavy pattern. And if we make the kernel property vary in space, we can make the orientation of the pattern also vary in space. And we can even use the frequency to make the scale of the pattern vary in space. So the key idea for us was to use this Gaba Noise and to find a way to extract toolpaths from it. And using the different orientation and to orient the toolpaths and the frequency to control on how much space they are between each other. However, Gaba Noise has one main limitation that we have to go into. It's the local loss of contrast. So the local loss of contrast is those gray area you can see here on the screen. And if you threshold the noise at its mean value, so here it's 0, we don't see any problem. But if we threshold it at any other value, we can see that we have this non-homogeneous pattern that we might want to avoid here. Right. So now, how to fix that exactly? So to fix that, we introduced the procedural Phasor noise. Here, if we look at two kernels and we mix them together, we can see that already we have this local loss of control in the middle of the kernel. And if we decompose a bit the different part of the kernel, and if we look at the kernel sum and the sum of Gaussian, we don't see an unexpected loss of contrast in the sum of Gaussian. So in fact, it means that it must come from the sum of sine wave inside. And if we look at it, actually it is. What's happening here is that the two sine waves are slightly phased out, and so they create a destructive interference in the middle. To fix that, we choose to focus in each point of the space and reformulate our sum of two kernel with just an intensity multiplied by a sum of two sine waves with different intensity. Here we limit the case to a single frequency and single orientation for simplicity. And so if we reformulate it like that, we can actually use what it's called Phasor Addition, which gives a name to the paper. And the Phasor Addition states that if you have a sum of two sine waves with different intensity but the same frequency, in the end, you can reformulate that with just a single sine wave and one intensity and one phase. So if you generalize that to an infinite sum of sine wave and with different intensity and phases, a bit close to what the Gaba Noise is, we can reformulate that to an intensity times a sine wave also. Thus, in the end, we get this function that also describes the Gaba Noise, which is an intensity field, which is a function of x, a phase field, which is a function of x, and just a sine wave in the middle. And if we just remove this sine wave, now we have a perfectly oscillated pattern. And the nice thing with this method is that actually we can just replace the sine wave with any periodic function we want. So for example, a sawtooth function or a gate function, so much closer to what we wanted in the first place. Right, and of course this works with kernel with different frequency and orientation, but for that I will ask you to refer to the paper. So let's see some results now. So first, let's look at the control we still have with this method. So a very important thing for us was to keep the control Gaba noise offered. So here you can see we have still the control on the scale or the frequency. We can play with the profile function of the noise with this direction. And also we can mix all of that together. We can use that to create nice effects of displacement onto the surface of object too. And we can also fabricate that, which is why we are here today. So here are two different examples. So the first one in orange is a test we do to visually recreate something close to a bone marrow. And the two other examples are actually a mix with two different materials. So the dark one here is a bit stiffer, and the lighter one here is flexible. And so when you mix them and you make the ratio vary between the two, and also their orientation and frequency, we can get interesting results. However, the problem was here that mixing two different materials was a bit hard, and they were not bonding that well, so we did not pursue it too much. Also, a cool thing that I like to mention is that this Phasor noise was in the last Star Wars movie. Here it's used to do the sand, right? Because it was integrated in professional rendering engine. Now, let's go back to the toolpath we wanted to extract. If we just threshold the noise using a rectangular function, here we can see that we have something that we could exploit, but it's a bit too, it's not that regular enough so that we can print it. It won't print well if we just extract contours and print them this way. So we had to come up with a way to regularize this problem. Right. So to understand a bit, first, let's talk about the singularities. So singularities in this noise will look a bit like this. And in this case, actually, we have one frequency and one orientation. So we know the ideal solution, which is a simple oscillation here. And if you remove that from the original noise, we get this pattern, which we call a phase field. And if you put the phase field close to the noise, we can see that the same singularity will appear in both of them. So it means that we can measure the energy of the singularities using this phase field here. So by just taking the gradient, we get some information of the singularities. So how do we fix that? Our first approach was, so we came up actually with two different approaches that works well together. So our first approach was a sampling approach. So if we just take to kernel, you might already see the problem here. It's because the kernel are slightly phased out. So the simple solution is just to phase them correctly, and we are done. However, when we have a lot of different kernel with a lot of different orientation and frequency, it's not that simple. And to fix that, we came up with a nice algorithm that can regularize them. So right here. So here you have an example of the regularization in action. It's and as you can see, just after a few iterations, we have a nice result. Now, the second approach. So the second approach was to study a bit more the signal of what we got. So if we go back to a simple example of one direction and one frequency for noise, and we still know the ideal solution here. So if we carry it out from the noise, we get the same phase field as before. And still, the singularities are always aligned with the problem, the pinching in the phase field. So the idea was to simply filter this phase field with a Gaussian function, and then to re-inject the sine wave in it. so that we get a cleaner noise. And if we increase the filter, we get an even better result. However, when we work with multiple kernel with different orientation and frequency, the phase field is not that well defined. So instead, we integrated the filter directly in the kernel, which now look like that. But for more detail, I will ask you to refer to the paper. So now, if we look at some results, we see that just after a simple filtering, the stripes look already way better. And if we apply also the regularization algorithm, we see that we have even less problem now. Of course, some singularity remain, but when you have diverging field, it's a bit mandatory to have them. Right. So if we look back at our example, and we look now at how it looks once we apply our algorithm, you can see that it's already way better. And a nice thing is that we were, as we can measure singularity, we were able to measure the improvement of our method. And as you can see, just after a few iterations, it's already way better. So now, how do we extract the toolpath that we want to print? So as a reminder, when we want to print something, we need to use a 3D object to compute slices and then to compute toolpaths inside this slice. So how do we go from this pattern to a set of edge and vertices that we can use to print? And so our solution to do that was to use the sawtooth function, which is a linear ramp between 0 and 1. And using that, we can easily define an ISO value that we want to extract. So thus, we already have a good definition of these trajectories. And so to extract them, we approached the problem a bit like a matching square algorithm. So in each point, we discretize the space with a regular grid. And in each point of this regular grid, we sample the field. And then on each edge of this grid, we check whether the ISO value cross the edge or not. Then we carry out all the edges that does not cross. And as the sawtooth is a linear function, we can simply do a linear interpolation to get the right values here. And then we simply have to reconnect them all together, and we are done. We have our trajectories. So here you have a bigger example. But as I said earlier, we might want to change the deposition width, for example, to spare some printing time. And so we need a way to measure afterward what is the spacing of this trajectory, such that we can adapt the flow of the printer. So to do that, we introduce an orthogonal Phasor noise that we will extract a bit in a similar way. And when we combine it to the first set of trajectory, we can see that it creates this kind of square-like pattern here. And using this, we can actually define a graph, which will be fairly useful to solve our problem, because if we just look a bit closer, so if we say we want to print the red toolpaths here, we can use the size of the green arrow locally to know the deposition width and so the flow that we need to use. And actually a nice trick that we use to do that is to compute both of those trajectories at the same time. So to do it quickly, we will apply the same methodology of sampling, and we will remove all the edges that does not cross any of the two values we want here. And using the same linear interpolation, we will find all the points we are interested in. So the green one are from one of the set of trajectory, and the red one are from the other. So yeah, I can remove the image in between so that you can look a bit better. Right. And so now we can just reconnect them all together as earlier. And the nice thing is, if we keep track of which cell created which segment here, we can only do the intersection in the cells that produce multiple segments, so that it reduces a lot the computing time. Right, so now we have a graph, and we can just apply a simple decimation algorithm on it so that it can be a bit more lightweight. And keep in mind, this decimation is not will not affect too much the toolpath because we are a tool-based scale at this point. Now, if we put back the two Phasor noise back, we can see that it matched quite well. So let's see some results now. So first, we have the Qtocto that we like to print in 3D printing. So here you can see that we printed it, and you can also see the preview of the trajectory we did. And as you can see, it's fairly well packed. There is not much porosity inside. And also, we use a larger deposition width in the middle of the Qtocto such that it reduces the printing time. We also apply our method by organizing the filament deposition direction such that it could improve mechanical property of the piece. We can also use the orientation provided by the Phasor noise to affect the way a piece will look like once printed. So here you have one example where we try to do a nice effect on this surface. And we can even do that, a bit of the same thing to alter the way light will bounce off our object. Right, so now we had another problem that we wanted to solve in dense infill. That is the dense infill consistency. So usually in dense infill, when you send the same input for two different slices, you will get the same result. And thus, if you have defects, they will always be in the same place. And so this will lead to error accumulation. So here you have an example of when we generated the Qtocto for the first time. And as you can see, this error accumulation will create long cavity inside the print that we want to avoid. And so our approach for that was to use a staggering strategy. So staggering here means that we will slightly shift the trajectory of every odd layer such that if there are defects, they will be also slightly shifted. And nice thing with Phasor noise is that we can do that quite easily by simply applying phase shift onto the profile function. So here you have an animation. Right. And we can also do that on the both Phasor noise we use to generate the graph at the same time, such that it will move even more the singularities. Right. And so in the end, we are able to produce a lot of different graphs for the same input values, such that we can use two that are shifted of half the deposition width to get a result we want. And so here you have an example where you can see that all the singularities that remain in the field are shifted every odd layer. Here's a bigger example if you want to check. So now let's see what the toolpaths look like now. So if we look back at our Qtocto, now that we apply staggering, so the first one, we can still see the cavities, and second one appear a bit more the cavities appear to have been broken down. And if we look back actually and do close-up, we can see that it's true, the cavities are not, the defects are not aligned anymore. So of course, we try to test our application here. And so we did first test, which was to test if the alignment of the toolpath was important for strain. So here is the mechanical specimens that we used. And here are the two tests we did. So here you have toolpath directions that are indicated and the strain direction. And so we had two tests, orthogonal and align. And what came out of this test is that actually for PLA and for the condition we did our testing, the fact of aligning the fibers of PLA with the strain direction was important, as it raised the Young modulus and increased the elasticity length of the specimen. Right. Of course, we wanted to measure that to the same kind of measure for the staggering. However, it's a bit hard to, it was a bit inconclusive. And the reason why these singularities will appear where the field of direction diverge. And as we used only single direction in the whole piece, they were not so much problem to fix. So the measurement was not conclusive. So a second thing we wanted to do in this work was to work on more sparse structure, but that keeps the idea of strongly oriented patterns, a bit like fibers. And our base structure to do that was this one, which is what we call a diamond shape structure. And it's fairly interesting because in 3D printing, it will be fairly flexible, as you can see here, in one direction, in another one too, and in this one it won't be. So it gives you a strong anisotropic response here. Also, it was also very interesting because this structure can be oriented a bit however you want in space, as long as you don't make it roll here. And so to be able to generate that, we use two sets of regularized Phasor noise, a bit similarly to what we did in the previous work. And we mix them together to create some local parametric space on which we apply a diamond cell pattern, on which we apply contouring algorithm just to get the walls that we wanted to print. And then we just had to transform them into tool passes such that we can print them here. And so now for some results. So we have a video, and as I said earlier, it's quite strong in this direction. I don't know if you see, flexible in this one, right? And we did multiple tests with that. So here is an example of spirally orientation field, and as you can see, it will impact interesting deformation in the results. Here you have an example of a joint we try to do, where the joint can only bend in one direction. So here is an example of a plate we did where if you press on it in one direction, it won't bend, but in the other one, it will behave a bit more like a grip. Okay. So here's an example where we try to mix different orientation at the same place in the material to create some isotropic behavior. So from one side, it's fairly irregular, and in the other, it's completely chaotic and use completely random orientation. As you can see, it will change a bit the behavior of the material. Right. So here is an example that I like a lot, which is a knee that we printed, where we use different density inside to create bones, and we oriented the material such that it recreates the bending of a knee. I have an example here. Well, here are the players we did. So just by playing with the different parameters of our method, we are able to use to create this player that is still working right now. Right. So now let's conclude this talk. So during this work, we provided new normalized procedural noise, regularization process to create the clean stripe we wanted. We produced a new method to compute dense infill while following orientation, and also a new method for sparse infill to generate flexible structure. So now in the future work, what we want to look into is to look into simulation, because a very important thing for this infill we produce is to be able to simulate them. As first, it will help the designer because if he has a simulation, he can have a feedback before printing. And also it can lead to inverse design, because if we have simulation, we can formulate an objective function that we don't have now. Also, a thing that we like to go into is that you noticed the graph and the structure we create can look a bit similar to some result from quad meshing. This is something we would like to know a bit more about, because we would like to know if it's a coincidence or if there is a deeper root to this connection here. So thank you for your attention. If you have any question, be pleased to ask them now.
Thank you very much for the talk. And we have some time for questions from the audience. And the first question I would like to ask is that the phasor noise looks like a visualization of a vector field. Did you thought of what are the limitations of vector field that could be visualized with the method?
Yeah, it actually does. Limitation. I guess we could mix different phasor noise to get like 2 3D vectors filled. The main limitation here is you only have you will only have like a vector, an indication of a vector locally. You don't have the global parameterization yet you need sometime with this type of application. This is one of the main limitations we have now.
Then there is a couple of hardware-related questions. And the first one is, what kind of material do you use for all of these flexible prints?
So these flexible prints were printed, if I'm correct, with Ninja Flex material, about 85A of Shore, if I remember well. And they were printed on a CR10 printer that was a bit modified to have direct extruder.
And which printer is it based on? Do you know?
The CR10? I use the CR10 printer, which
okay.
Creality. It's
the Creality one.
Yeah, it's not a very expensive one actually.
Oh, I see. And how was the printing time affected by changing the structures into?
Well, it's hard to say because at first we had quite some trouble to print 85A filaments because the extruder was always stretching the filament, the flow was hard to control, and so on and so on. So at first it was, we had to reduce a lot the speed and to get our results. But now we gain much more experience with our engineer on printing with such kind of filament. And so now we are able to print much more faster. But at first it was fairly difficult to print.
And the difficulty was mainly because of the material itself, or was it also from trying to use your own G-code to drive the printer instead of the supplied slicer?
We used ISSL because we developed it in the team. So I had access to the source code. So most of the G-code was then done by SSL. So this was not really an issue. There was some calibration to do, of course, but this was not the main issue. The main issue was really the material we use. For example, this kind of filaments they tend to get they tend to get wet a bit and to print worse. So we had to constantly dry them, for example. So it was some issue here.
And the last question is about the examples that you were showing. Right. Were these hand designed, or did you somehow optimize their functional properties?
No, they were all hand designed using ISSL. We have a painting tool in ISSL that allows to paint the direction you want in the object. And so I did some myself. Our designer helped us a lot with the examples. And the thing is, just after a few iterations, you start to get the end on the structure and to be able to design correctly. So there is always some adaptation to do, but it's not that hard to design with them.
Okay. Thank you very much for staying for the questions and for the talk. And now we will move to our postcard discussion where you would still stay with us for a little bit, but it will not be streamed anymore on YouTube. So thanks also, Sylvain, for attending.
Thanks.
Goodbye.
Goodbye to everyone. Right.
Okay.